Good morning everyone. This is Mr. Swapnil Bapusa Verwade, lecturer in Institute of Technology Polytechnic Yatra, Ichalkaranji. I am here with my new lecture on heat treatment process. As you know, we have started our sixth chapter, that is heat treatment process, and we have already covered the three lectures on the same only. Okay, and in that we had covered what is my heat treatment process, their types, what is the limitations, what is the purposes, what is the applications. Okay, and in the last lecture itself, we have started the first type, that is annealing process, and in that we have covered its own four types. Okay, so in this lecture we are going to deal with the two things, that is normalizing process and hardening process. Okay, so see, the subtopics of the lecture are like: first, normalizing process. In that we are going to see the three things, that is process, the purpose and the application. And second, hardening process. In that again we have the three things, that is its own process, purpose and application. Okay, so this will be our overview of this lecture. Okay, so we will start with the normalizing process. See, as you know, any heat treatment process have the three steps. We first heat the material, we hold the material, and we cool the material in any media. Okay, and the basis of that cooling media, we divide our heat treatment process into four types. Okay, if I cool the heated material in furnace, it is an annealing process. If I cool the material in air, it is normalizing process. If I cool the material in water or any liquid media, this will be a hardening process. Okay, and if there is a high hardness, then we can have air cooling of the heated material or the hardened material. It is a tempering process. Okay, so the heat treatment process is always have its bifurcation on the basis of cooling media. Okay, so here normalizing process, see, in the first line itself they had said that normalizing is also called as air quenching, and this quenching is nothing but a cooling. Quenching is a technical term for the cooling. Okay, so normalizing process, we have the air quenching, we can say the cooling with the help of air. Okay, so the temperature zone that is heating at 50 degrees Celsius above the A3 and AC. As we know, in iron carbon equilibrium diagram, on this diagram we have total 5 critical temperatures, or we have the total 5 temperature lines as A0, A1, A2, A3 and ACM. Okay, so in this we use the A3 and ACM line. So see, this line will be a A3 line, that is from 727 or 723 degrees Celsius to 910 degrees Celsius, and this line will be the ACM line. This is from this 727 to 1147. Okay, so this is ACM line, this will be a A3 line, and this blue color zone is nothing but your temperature zone. Okay, in this zone only we are going to heat the steel. If we have the steel with 0.4% carbon, then we are going to heat it up to in this range. Okay, if we have 0.6% carbon steel, then we can heat it in this range. Okay, so this blue color indicates what is the zone to heat it. Okay, so in this temperature zone only we heat the steel. It is just depend on its what amount of carbon it have. Okay, if you have the 0.2% carbon, then we are going to heat it at a higher temperature. If you have 0.4, then we will heat it at a lower temperature, but it is always above the A3 temperature. Okay, so see, in this process, as we know, there are three things: heating, holding and cooling. First, that is heating of a steel at temperature 50 degrees Celsius above the upper critical temperature, that is this line A3, it is upper critical temperature. The temperature is from 727 from to 910 degrees Celsius, and above this we will heat our steel, and this blue zone will be of normalizing temperature zone. Okay, and see what is written here: above A3 and above ACM. Okay, above ACM means this line will be your ACM line. Okay, then see, above ACM means from 727 to 1147 degrees Celsius. Above it, for 50 degrees Celsius, we will heat our steel. Okay, so see here in this temperature, this is temperature and time diagram. First, we heat the steel up to some temperature above A3 and above ACM. Then, for some time, we hold the steel. Holding is used to have a uniform structure. See, when we heat any material, it first get heated from outer side only. Okay, its inner side or the inner point will not get heated at the same temperature. Okay, so at initial at initial of holding process, there is a temperature difference between the outer surface and the inner surface. Okay, so we given a holding period to have same temperature throughout the material, and when we have the same temperature throughout the material, and then only we get the uniform normalized steel at the output. Okay, if we have the different If you have the heterogeneous material, then you get the different properties of a single material. Okay, so holding process is to have the uniform structure of a material in the sense of temperature, because we are doing the holding process at a higher temperature, so that that material must have the same temperature at its every point. Okay, so next, holding the steel at this temperature for some time to get homogeneous structure, to get the uniform structure. Next, cooling the heated steel in air up to room temperature. So this will be the process, that is cooling using air. Means we can cool our heated steel from above ACM to up to room temperature, that is up to 20 to 30 degrees Celsius, and at this end we will get the normalized steel. So this whole process is called as a normalizing process. Okay, so see, next, in normalizing, there is a complete phase transformation and fine grain structure is obtained in casting, forging and roll by. As we know, here we heat the material above 727 degrees Celsius, because that blue zone is above the 727 degrees Celsius. So there will be a phase transformation from perlite to austenite. So there is a complete phase transformation. See, here we have written that there is a complete phase transformation. As we heat any steel above 727 degrees Celsius, there will be a transformation from perlite to austenite, and when we cool it again back, then there is again transformation from that austenite to perlite. So there is a complete phase transformation. Okay, next, then during air cooling, the rate of cooling is faster than furnace cooling. What is mean by rate of cooling? It is a cooling speed. As we know, in furnace it required more time for a cooling. In air it required low time period for cooling. So it is the rate of cooling is faster than annealing or furnace cooling. Okay, so next, at lower temperature, austenite transform into fine perlite structure as compared to annealing. In annealing we get the coarse perlite structure, that is somewhat softer one, and here we get the finer perlite structure, which is comparatively harder structure. So in normalizing we get harder structure than that of annealing. Okay, next, because of finer structure, normalized steel becomes harder than the annealed steel. In annealing, at the output we get coarse perlite, and in this we get fine perlite, and always finer perlite is more harder than that of coarse perlite. Okay, next, purpose of normalizing, it produces stronger material than fully annealed material. Means stronger material means you have some sort of high hardness, because there is a change in cooling rate. See, always remember one thing, your hardness will always depend on your cooling rate. If you have the highest cooling rate, fast cooling rate, your hardness will be higher. If you have the low cooling rate, hardness will be lower. Okay, so hardness of the material and cooling rate is directly proportional. Means cooling rate is low, hardness will be low. Cooling rate is higher, hardness will be higher. Okay, so these both are the directly proportional to each other. Okay, next, to improve properties of steel. To improve properties of steel means you can increase the strength, its toughness, its somewhat ductility. Okay, so it improves some properties of the material. So some mechanical properties of the material. Okay, it refines the grain structure. Grain structure means there is a change in crystal structure, because up to 910 we have the BC structure, up to above 910 we will have the FC structure. So there will be change in crystal structures at some above temperatures. Okay, so next, we have greater or the better surface finish from this process. Okay, it produces homogeneous and uniform structure. As we know, there is a holding process in between the heating and cooling process. So in this, it produces the homogeneous and uniform structure at holding process, and the same we will get at the output. Okay, next, strength and hardness is increased. Strength and hardness is increased because as it is a normalizing process, it have the high cooling rate as compared to annealing. It will have the high hardness. As it is have the high hardness, it will have the high strength. Okay, next, it have resistance to brittle fracture is increased. What is a brittle fracture? Brittle fracture means, we can take an example of chalk. When we break the chalk, it have the sudden failure without any pre-showing of the failure. Okay, if we bend any 2 rupees pen, okay, if I take a 2 rupees that plastic pen, okay, if I bend it, then it will show some bending structure. Okay, but if you break the chalk, it doesn't show any premature failure. Okay, it suddenly get failure. Okay, that is nothing but a brittle fracture. When we normalize any steel, it will increase the resistance to brittle failure. Means if we have any normalized steel, then it doesn't get have a it doesn't have a brittle fracture. It will tend somewhat, it will have some bend, and then it will get fail. It doesn't have the sudden failure. Okay, next, applications of normalizing process. First, for rolled and cast steel to refine the grain structure, for carbon steel to improve the microstructure, for low and medium alloy steel to increase the hardness on high stressed material, to reduce the stress on welded structure for uniformity or homogeneity. Okay, so next will be the hardening process. As we know, hardening is the heat treatment process of steel in which increase in hardness by quenching. Quenching is the technical term for cooling, and in hardening process we always use the rapid water cooling, or we can say rapid liquid cooling. Okay, so that in hardening process there is a highest rate of cooling. As you know, as I said earlier, the rate of cooling and hardness are they directly proportional to each other. So there is a high rate of cooling, there will be a high hardness. Okay, so temperature range. Here for temperature range, for we have divided into two things, that is for hypoeutectoid steel means from steel from 0 to 0.8 carbon, and for hyper means from 0.8 to 2% of carbon steel. Okay, so see, for first hypoeutectoid steel, it is heated above the A3 line by 30 degrees Celsius to 50 degrees Celsius, that is above the 727 degrees Celsius and above the 910 degrees Celsius. And for hypereutected steel, it is heated above the A1 line by 30 to 50 degrees Celsius. In this next slide, we can see the temperature zone. See, in normalizing process, we have V-type structure. Okay, above A3 and above ACM. In this, we have somewhat in this up to 0.8% carbon we heated above A3 line, and from 0.8 to 2% we heated above the A1 line. Okay, so there is some slight change in the temperature zone. Okay, here also we have again three things, that is process. We have heating a hypoeutectoid steel. Hypoeutectoid means from 0 to 0.8, this is hypoeutectoid steel. We heat the steel above this A3 line by 30 to 50 degree Celsius. That is from 0 to 0.8, this is a low and medium alloy steel. We can heat this steel above this A3, and this dark zone will be the hardening heating range, or the we can say hardening temperature zone. See, for 0.6% carbon we can heat the steel at this zone. Okay, for 0.2% carbon we can heat in this zone. Okay, so this will be the zone for temperatures. Okay, next, from 0.8 up to 2%, this will be the hypereutectoid steel, and for this we will heat above the A1 line. For this 0.8 to 2%, there is a constant temperature zone. Okay, because A1 is a horizontal line. Okay, next, again we have the holding process. Hold at this temperature for some time to get homogeneous. As we know, when we heat any material, it gets first heated by its outer surface, then that same heat will be get conducted to the inner surface, and that conduction of it from outer surface to the inner surface will get some time, and that time will be the holding time. Okay, and the holding process is required to get the uniform structure. If we get the uniform structure at the holding process, then we get the uniform and homogeneous structure at the output outside. Okay, next, cooling is the heated of steel at a very high rate by using water. It may be oil or any other liquid media. Okay, so in hardening process we always cool the steel in any liquid media to have a fast cooling rate. Okay, next, purpose of hardening. As you know, hardening it will increase the hardness, toughness, then it will decrease the malleability, ductility, all these things. Okay, in general, just we see the one by one. Harden the steel to resist the wear. Okay, as we increase the hardness of material, it will decrease the wear and tear of the material. Next, enable the steel to cut other material. As we increase the hardness of material, so that it can cut the other material. Increase the hardness and brittleness. Okay, see, in general, when hardness increases, with that brittleness also get increases. Okay, next, increase wear resistance, then increase cutting ability of steel. So in general, the hardened steel is always used as a tool to cut the outer material. Okay, and it developed the best combination of strength and compression. It developed the best combination have a strength and compression. Okay, next, degree of hardness produced will be depend upon. See, when we cool the material with a very high rate, okay, then its hardness will depend on some things. Just like we have first composition of steel, it may be a low carbon steel, it may be a medium carbon steel, or it may be a high carbon steel. Then next will be the nature and properties of the cooling media. Okay, see, as a liquid media, we have 4 to 5 things. We have water, we have oil, we have brine, we have molten salt, we have water and air spray, and with this also there is a change in hardness. Okay, next we have cooling temperature. Next, size of the object to be cooled. If size will be small, cooling time will be less. The object is big, cooling time will be somewhat more in seconds only. Okay, rate of cooling, if there is a fast cooling, high hardness, then there is a somewhat optimum rate of cooling, there will be optimum hardness. Surface condition of metal like impurities and scale, and last one is the uniformity of austenite phase. Next we will have quenching and cooling media. See, it is a media into which heated metal objects are placed in order to remove the heat from objects. Means it is a media in which we can cool the heated material in the hardening process. Total we have 5 medias, that is water, oil, brine, molten salt, and water and air spray. Water in general, as we know, we can cool it. Oil to have some viscosity. Brine is nothing but a solution. So this is for our today's lecture. Oh, okay, thank you one and all.